one of the problems with this is it's most of the stuff that we've been playing with, like chi-square, when we really took a look at how you calculate it, odds ratio, relative risk, and stuff like that. Mathematically, they're pretty simple ideas, really, when we actually did the calculations. Correlation is that something that you talk about like in everyday language. I mean, it's a word you use all the time. Oh, well, this seems to correlate with something else, or I see a correlation here, or something like that. You use it every day practically. But correlation, and especially its ugly big brother regression, is a much more complicated concept than what we were looking at before. But it's much more useful too. Okay, but we're going to try and strip it down a little bit with some examples, so it gets a little bit simpler. How many of you guys like kind of like a little bit of that went over your heads there? Yeah, a little bit, right? So it is a little bit complicated. So let's start with correlation. In correlation, we're looking for an association between two variables. What kind of variables are we talking about now? Numerical, right? We're looking at two numerical variables. This is important because when we get to the midterm exam, we were looking at a lot of concepts about data types and different the normal distribution and how normal distribution behave, central limit theorem, and how samples behave, and so on and so forth. This time around, we're actually, for exam 2, and for the project, we're actually applying statistical tests to situations that we want to find an association between a couple of variables or prove something, right? So it's important that we start off with understanding what kind of data types we're working with, because the data type determines what the appropriate test is going to be. Like if you have two categorical variables that you're working with, or if you have a categorical variable and a numerical variable, and so on and so forth, and how many values you have, analysis of variance and t-test, and so on and so forth. So I think like I'm going to set up 2 sessions, like an evening session over the next 2 weeks before the exam, an evening session and like a Saturday or Sunday morning session. I'll put up a Survey Monkey where you can put like your preferred times, and I'll try and accommodate as many people as possible. And in any case, I'll try and record it so that it's available anyway. But a lot of what comes up at this time of the semester is that, gee, I want to look at these two variables. Am I using the right test for this? That's another reason why we want to get like kind of a preview of what you're going to do on the project, because you want to make sure that you're not applying the wrong kind of analysis to it. So let's talk about correlation. Correlation, pretty simple concept. Not always in practice. In practice, though, it gets a little bit more complicated. For starters, I think you heard before that when we work with correlation, we don't necessarily, correlation doesn't necessarily imply causation. Okay, so I'll give you an example. There's a correlation between the number of firemen that respond to a fire and how much damage there is, right? Makes sense. Right? Why does that make sense? Because bigger the fire is, more firemen, more trucks are going to respond to that fire. So it's a bigger fire, there's going to be more damage. Okay, now I know some people that are firemen and they cause a lot of damage even in their private lives, but so there could be some association just with the number of firemen, but for the most part, it's usually the size of the fire. Yes.
Here's a fun one: the number of motorboat accidents and the ice cream consumption.
Right, there you go. Okay, now as a matter of fact, it's interesting you should bring that up, because there is a guy that has spent, it's kind of a hobby for him. He looks at these things called spurious correlations. Correlations that clearly are not real associations, but are just associations by chance. There's not even a real reason. Why would ice cream consumption have anything to do with motorcycle accidents? And I think I put a link on Blackboard. Let me see if I can't find it, just so I can show it to you quickly. And then I'll get back to these. I'll get back on off of my tangent. Oh, no kidding. Let me get onto Blackboard. And he's got a couple of great examples. Here we go. Oh, here you go. The more people eat cheese, the more people are killed by their bed sheets. And we have a few charts right here. Here's a year-to-year number of people that consumption of cheese. Oops, I'm getting commercials here. Consumption of cheese. So I can't get this to go away. Consumption of cheese versus the number of people that were strangled by their bed sheets each year. Boy, it looks like there's pretty strong association there, right? We've got the per capita consumption of cheese. Let's see. Let's see if we have a couple of. I have a link to his website on Blackboard that'll give me some more. Let me try another one. Shouldn't have done that. Let's go back here. No problem with it. Slow loading websites. Here we go. There's an interesting one there. Number of people who drown by falling into a pool, and the number of correlates with the number of pictures that Nicolas Cage appeared in each year.
No,
Yeah, so there you go. You have a whole bunch of the age of Miss America and murders by steam, hot vapors, and hot objects. And unfortunately, the actual charts are not coming up here, but the actual charts will show you like really these amazing correlations. But at any rate, so we can have these associations, but they don't imply causation. They're not very useful that way. So when we look at correlation, what we're looking for is an association between basically one number, the value of one variable, and the value of another. Okay, so each one of these pairs of numbers are associated with a particular subject, with a particular measurement, and so on and so forth. Like, for instance, for you, your age, your BMI, your weight, your body temperature, and so on and so forth, those are all numbers that are associated with you. So we can choose any two of those variables, say age and body temperature or something like that. And we can look to see if there's an association between someone's age and their body temperature. And the way we're going to do that is for each person, each subject that we're going to sample, we're going to measure their age, we're going to ask them their age, measure their body temperature, and that's going to become a coordinate on the next Y graph. Right? So, okay, and for when we're talking about correlation, it doesn't matter which one I call the x-axis and which one I call the y-axis, because I'm not assuming there's any kind of causality involved here. When we get into regression, by practice, we're gonna look for we're gonna call the x-axis, we're gonna call that the independent variable, and we're gonna call the y-axis the dependent variable. But that's only when we get to regression, because when we get to regression, we're looking for some sort of association that's associated with causality. So if I take each person's age, 20, 30, 40, 50, and I'm going to assume for a second that maybe body temperature goes down over time. This particular person might be 22, let's see, 98, 99. This particular 25-year-old, their body temperature might be, say, 98.6, pretty normal. Next person, an older person, maybe a little lower, a little lower, a little lower, and so on and so forth. And we might start to see an association. That's where that's where we generate these scatter plots. We're just creating a dot for every coordinate that represents those two numbers for that particular subject. Like, for instance, this person's age is 25, the x-axis, and this person's temperature is 98.6, the y-axis. And each one of these dots represents a coordinate. And what we're looking for is an association. You can kind of see it here. And in fact, you can kind of imagine drawing a line through here, right? That would bisect all of these different outcomes. You would not expect all of these different outcomes to fall directly on that line, because that line, since it's a straight line, that we would have to have a perfect association between age and body temperature in order for all these values to fall on that line. That would be basically a perfect correlation. Okay, so now the way I'm going to draw that line is I'm going to look at how far away each one of these values is from that perfect line. And I'm going to draw a line that I might have chosen a line like that or a line like that or something like that. I'm going to choose a line that gives me the total. I'm going to take the square of the differences, the excursions from that line, okay? And I'm going to take the square of those excursions. I'm going to add them all up, and I'm going to use the line that gives me the smallest numbers for all of those squares of those differences. That's the idea of least squares, okay? So that's what we're doing there. That's how we're developing that line. Now, you guys remember from algebra that a line, formula for a line, the algebra version of it that I remember is y is equal to mx plus b. Okay, and where b is what? That's the y-intercept, right? If I make x, if x is 0, right, that means that y is just equal to b. So that's where this line crosses the y-axis. That's what b really is. It's just that value right there where it crosses the x-axis. M is the slope of the line, okay? And the slope of the line is going to be the change in x, change in y over the change in x. Delta y over delta x, right? So in other words, if x changes, looks like this slope here, x is larger. So let's say x is, how many years would that be? Let's say x is 10 years, and y is let's see, as x goes larger, it's positive. As y as x gets larger, y gets smaller, so it's going to be a negative number. It looks like it's maybe 0.5. So the slope of this line is 0.5 over 10, or in other words, it's 0.02, but it's actually a negative number, negative 0.02. So that number goes in front of that x. So this line is represented by a formula which is negative 0.02 plus the y-intercept. I'm going to call that 99 degrees. That equation represents that line. If this were a real association, and we had evidence that would suggest to us that there is some reason to believe that people's body temperature goes down as they get older, we could use that line predictively. In other words, let's say that unfortunately, body temperature is not very invasive, right? So in other words, these days you point at something at somebody's forehead to get their body temperature. Let's say that we go back 100 years, and it's a lot harder to have an instrument that takes body temperature and stuff like that. But you wanted to guess at someone's typical body temperature based on their age. Well, you could use this formula to predict what their body temperature is based on their age, which is easy to determine by just asking them. Okay? So there's some reasons why we might want to use this. Besides even, we might want to use this predictively, even besides understanding how one variable impacts on another. The other thing that this helps us out with is that by looking at this slope, the y-intercept really doesn't tell us very much. In fact, the y-intercept in a lot of cases doesn't even make sense. So, for instance, if I were looking for a correlation between, say, blood pressure, between say height and blood pressure, right, where height is the independent variable and blood pressure is dependent on the height, dependent variable. And I said, okay, there is an association there. Maybe it's positive. So blood pressure, you get taller, blood's got to pump higher and something like that. So it's going to be a positive association. Well, that y-intercept is going to be where height is equal to 0. Doesn't even make any sense, right? Because nobody's height is 0, right? So that y-intercept really doesn't tell us all that much. But the slope tells us something very important. The slope tells us how big the association is between how much you increase one variable and its impact on the other variable. And once you know that, you have a pretty good understanding of how some intervention or some change that you might introduce is going to impact the other variable. In other words, if you tell people to lose weight, how it might impact their blood pressure, for instance. Because you can look at the slope and see, well, people that lose 10 pounds or 20 pounds or 30 pounds, that I can predict that their blood pressure will go down by about this much or something like that. and maybe you can compare that to the slope from reducing saturated fats in a diet or something like that. You could say, the slope here is not as great, so the impact of doing this is the resources should really go into losing the weight rather than dietary changes, maybe, or something like that. There's a lot of ways you can kind of look at how you might apply this. But that's the deal here, is what we're looking for is we're looking for an association that is demonstrated that by these scatter plots that we can then quantify. So I'm going to open up, I'm going to look at we have an exercise. And in this exercise, we look at 10 patients between 30 and 60 years old, randomly selected, and it's kind of a bogus exercise, but we have 10 pairs of numbers, and we're looking at age versus blood sugar. Okay, we actually have that same data set on Blackboard. You can download it. We're going to import that into SPSS. Open. Data. And age versus blood sugar. Not a real data set, just a made-up data set in this case. Okay, and here we have it imported in SPSS. Age is the first variable. Blood sugar is the second variable. I'm going to go to the variable view, and you can see they're both scalar variables. So I'm going to go back here to the data view. First thing I'm going to do is see if I can see visually if there's an association. So I'm going to go to Graphs, Legacy Dialogs. I'm going to go to Scatter Dot. And Scatter Dot is just simply asking it to plot all of these pairs of variables on a straight line. I'm going to click Define. Now again, if I'm just looking at correlation, I don't care about which I put into the x-axis, which I put into the y. So I'm gonna be a little consistent here anyway. I'm gonna put age into the x-axis because that's my independent variable. That's gonna predict the y, what's on the y-axis. Okay, it might come in a little handy if we get into regression or something like that. But really, I could work with this either way as far as I'm only interested in correlations. Let's see what this looks like. Okay, so how's it look? Well, it looks like, I don't know if you can see that very well if you're doing it on your own computers, but it looks like there's an association. As age goes up, blood sugar goes up. Okay, not all some of the patients, well, not so much, or so on and so forth. It's kind of like a grossly modified, a grossly engineered data set, but just to give you an idea of what this might look like. Well, now we can actually attempt to draw that line, that least squares line. And in fact, if you double click onto the chart, you can actually choose to add a fit line, which is the least squares line, to this graph, and it'll go ahead and add it for you. Not only will it go there and add it for you, but it'll actually calculate that formula we just talked about. Okay, we got to jump ahead of ourselves a little bit. So this looks like a situation where we have a correlation between these two numerical variables. Let's go ahead and actually measure that numerically now. You guys remember what statistical test that we're going to use? What statistic that we were interested in? What was it called again? Pearson's correlation coefficient, right? R, or rho, actually rho. Okay, so let's give that a try. Analyze, correlate, bivariate. That's one second. Oh, by the way, when you look at your version of SPSS, this is what you're looking for. See if you have binary logistic. Okay, if you don't have it, don't worry about it. You'll be able to use the cloud version of it that we have access to for that one test. So it won't be too annoying for you. I'll make sure you have the data set, whatever data set you need to work with. Okay, where was I? Correlation, bivariate. Okay, and again, doesn't matter. Notice it doesn't even ask me which is the dependent, which is the independent variable. I can just simply move it in there. And it's going to calculate my Pearson's correlation. That's what we wind up getting. I had to upgrade my version. They have these nice, pretty little tables, but they're kind of a little faint. Do this again. Okay, just so I can get it to pop up in the page here. I got another way to do this too. Ah, where'd it go? I lost it. Went to documents or something. Nope. That's interesting. Let's try it again. There we are. Oh, there it was underneath. Okay. So at least now I can load this up a little bit. Okay, let's take a look at that. All right. So let's see. What do we have here? The let's see. Pearson's correlation turns out to be a number of 0.821. Anybody remember what the range of numbers that we could have for correlation? -1 to +1. And the closer we are to either one of those is going to be the strength of our correlation. So this is a very strong correlation, 0.821. Okay, and it appears to be a significant correlation, right? Its significance is less than 0.05. Our sample size is 10. And it actually does it two ways. It actually does it for age versus blood sugar, and again for blood sugar versus age, the way that SPSS kind of does this all the time. When you correlated age versus age, it comes out to be 1. It's perfect correlation. They're the same number. So age versus blood sugar is 0.821. Blood sugar versus age is 0.821, which makes sense because there's no reason to think they would be different if you change them around. Yes. Okay.
The sensitivity -1, and you know when it's at, which is to both extremes.
Yeah.
That would be
that yeah.
Why
so something that has no correlation, that there's no association between this number. For instance, let's say your age and your geez, I have to think something that's really just has no association at all. Liking hair. Well, I don't know about that. If you have a lot of people that are my age have no hair, so I don't know if I'd pick that one because there are a lot of zeros in there. I don't know, ring size, let's say, or something. Your age and your ring size, right? Because you might have your hands might be any size, and it probably stayed about the same size your whole life, your hands, right? So your age and your ring size probably has no association. So we would expect that if we were to plot that on XY plot, a scatter plot, that it would just look like a cloud of dots. There was no reason, no association, no trend up or down, and that would have a Pearson's correlation of 0. Now, it's never going to have exactly 0 because it would have to be completely random to be 0. So it's always going to, you're always going to be a little bit from 0. The idea here is that number one, is it a significantly larger number than 0? And that's going to make the difference there is going to be, well, sometimes when we're looking at something that's really important, even a weak correlation might be something that we're really interested in. Like maybe there's just a, kind of like weak to moderate correlation between triglycerides and heart disease, right? But gee, we might want to treat that anyway because even though that's a weak association, so it can impact so many medical outcomes, right? So we got to be a little bit careful about making that judgment. But in general, if it's close to zero, there's basically little or no association. If it's close to one, it's a stronger association. So if it's positive one, it means they both increase. As one increases, the other increases as well, slopes up. And if it's a negative correlation, it slopes down. Okay? As the x-axis gets larger, the y-axis gets smaller, and it slopes downward. Now, what would you expect as the correlation? What would you expect to see that line look like if there's no association? The correlation is zero. Yes, horizontal line, right? That's approximately the horizontal line. Okay, so that would kind of be the definition, almost graphically, of a no correlation at all. Okay, so let's go in the next step. Let's actually take a look at this and quantify this association using regression. Okay, and I'm going to go up to SPSS again. I'm going to go to Analyze. Regression this time, linear. Okay, and this time it's going to ask me which is the independent variable because we're going to imply causation here. So our independent variable is going to be age, and our dependent variable is going to be blood sugar. Okay, so let's just give that, go ahead and just leave it at that and give this a try. Let's see what we wind up with. Well, actually, I'm going to get this whole thing. Let me get the whole thing. Okay, let's take a look at this. Okay, let's take first a look at what our coefficient, correlation coefficient. It's the same as we calculated before. It's the same calculation. Now r squared. If you do that calculation, you're just taking r and multiplying it by itself. If there's a strong association, you expect r to be very large, and since r squared is based on r, you would expect r squared to be a large number too. In this particular case, r squared gives us a window onto approximately how much of the variability, the change in one variable, impacts the other variable. So in other words, this particular analysis is telling us about 67% of the change in, as we increase age, the change in blood sugar is associated with that of the variable age. So age is going to be a very strong predictor of what blood sugar is. Again, focus data, but this is kind of an indication of, well, that large R square value means that this is a significant predictor for us. Okay, so if I go down to the next table, it does an evaluation. Well, I'm going to skip over a note, but I'm going to go down to the t-test down here. We want to know what, actually, I want to go a little bit further than that. Let me go down here to the coefficients and discuss what these numbers down here mean. Okay, so these numbers down here, the coefficients. Oh, come on. Let's take a look at this table. These numbers, SPSS has calculated the coordinates of that line, the values for that line. So our y-intercept is 17. Okay, our slope is 1.762. So basically, we've got an equation now where, let's see, what's our equation going to be? Our equation is going to be our dependent variable, which is blood sugar, is equal to 1.762 times age, our slope times that variable, plus 17.47. So we have an equation that represents that best fit line. Okay, so this is the important thing. This slope tells us that as we age, if we age 10 years, our blood sugar goes up 17. or on the average, it goes up 17. Or maybe we can predict that we think it'll go up 17 or something of that nature. Now, is that a significant, statistically significant? Can we trust that? It was a very small data set that we're working with. Is that association strong enough with the small data set for us to reject our null hypothesis that there's no association? In other words, our Pearson's chi-square is equal to 0. Okay, and our significance suggests that that is significant. We can reject the null hypothesis and say that there's an association between these two. So now, once I've done this, now I have a formula. Yes. I'm sorry. The significance. Oh, that's for the constant. Remember, that really doesn't impact us as much, right? Because a lot of times that y-intercept doesn't even mean anything. Like, for instance, in this case, what's the age of the person that has a blood sugar of 17? 0, right? Probably a study didn't even consider infants, right? It's only adults. So there's no data there. The other thing you should know about correlation lines and regression, they're only valid within the range of where you actually collected the data. So if you only included people from 30 to 60, you shouldn't extend that and assume that it's also true for people under 30 or people over 60. Okay, and in this case, the y-intercept, we're not really concerned about that because it's just a marker that helps us place that line. We're really concerned about the people that were actually in the range that we were working in. So now the next thing I want to take a look at is that we can go back now and look at each person that was in this study and see how well we predicted their blood sugar based on their age. Okay, and I'm going to go back into SPSS. I'm going to go to Analyze. I'm going to go back to Regression, Linear, okay, Age. So this time I'm going to sneak down. There's a lot of different choices that we can have in these various options that we have as well. We're going to be interested in plots as well in a little bit, maybe next week as well. But one of these is Save. I'm going to go into Save for a moment. It's a little bit different option in SPSS. It's not going to give us anything interesting in the output table. But it's going to give us some very interesting information in our data table. And basically, I can go in here and tell it, calculate the predicted values for each person that's in this study. In other words, okay, great. This person that was in this study, his age is 61, right? If you would use that to predict his blood sugar, what number would you have gotten? So I'm going to get my predicted values. Now, I can also tell it, give me the difference between that person's actual blood sugar and what the formula gave us. So I can see how much of an error I had there, how much of a difference there was. Okay, so I'm clicking off unstandardized. Unstandardized means I just want to know what the values are themselves. I'm going to say okay. Okay, let's see what we wind up getting. Okay, not too much information. Gives a little bit of information about the residuals, the standard deviation, the minimum, maximum, the mean residual, and so on and so forth. But the really interesting part of this whole thing is when I go back to the data table. We have two new variables there, right? The two new variables are the predicted value and the residual. And if you take a look at it, you'll see that the predicted value is 70. The residual is the difference between 70 and 75. Right? It's calculated that way. Why is that of interest to me? Well, let me take another look at this. Let me go in here and go into Graphs, Legacy Dialogues, Histogram, and I want to find a histogram of the residual values. I'm going to click OK. See how that plot looks for us. Well, there's so few values in here. It doesn't really help me very much. But one of the things that we're concerned about is that there's no particular association between being younger and blood sugar and being older and blood sugar. That the association that we're looking at is true throughout the range of ages that we're looking at. So what would we have expected to see here if it was a bigger database? What would we expected to see when I did a histogram here? We would expect to see the histogram for those values to be a normal distribution. In other words, we would expect that most of them would be pretty close to that line. In fact, I'm going to do this another way as well. You can see that the middle here is 0, and to the left is the number of values that were below no difference and above no difference. So we would expect to see a normal distribution. Most of the values for the residuals would be random, would be normally distributed on either side of 0, 0 difference. That would suggest to us that this is a valid association, and there isn't anything hiding in here in terms of confounders that might be impacting on people that are older than people that are younger. Okay, so I'm going to try this again with a larger database. Okay, let's see what else I have here. Okay, I'm going to open up violent crime. Okay, and this is 51 states in the District of Columbia, and it has the rates of violent crime, the murder rate, poverty rate, unemployment rate, so on and so forth. All numerical variables. Unemployment rate might be a percentage, the percentage of people with a college degree or that have some college, some measurement of poverty, the percentage of people below the poverty line, and so on and so forth. Let's take a look at the murder rate. Which do you think would have the strongest, which other variable do you think would have the strongest association besides violent crime? Let's leave that out, obviously. That would have the strongest association with the murder rate in these particular states. Want to go with poverty or single parent percentage, single parent families, unemployment? What do you guys think? Any opinions? What's that? Urban, right? I think it's a measure of whether something's whether it's an urban environment or a rural environment. It might be a per capita, like a population density measurement or something of that nature. I honestly don't remember. Huh? Try that one? No, we don't even know what that one is. We're not going to try that one. That seems kind of silly, right? Okay, let's try one that we know what it is. Let's try the unemployment rate. See if that has an impact on if there's an association. Okay, which one do you think would cause the other? I don't think the unemployment rate is going to be low because dead people don't work. I think it's the other way around. Right? I'm going to look at if unemployment has a impact on the murder rate. So I'm going to analyze. I'm going to go. Let's try correlation first. Bivariate. What's the first thing I should really do to evaluate this? Yeah, do a scatter plot first. Graphs, legacy dialogues, scatter plot. Okay, and let's do a simple scatter plot for starters and look at the association between murder rate and, say, unemployment. See if we see an association. Okay, and here we go. Does it look like there's an association there? It's kind of hard to see, right? Anybody see why it's hard to see there? Right? Because the scale here is compressed because there's one particular state that has a very, very high, it's an outlier, has a very, very high murder rate. So maybe I want to get rid of that one, right? And look at the other, well, where is that? What do you think that is? No, these are states, right? States in the District of Columbia, right? Not a particular city. It might have been Chicago this year if you're looking at cities, right? That's DC. That happens to be DC in this particular study. So I'm going to go back in here. Now I know you guys like to filter stuff, but I'm going to clear this because it's just quicker. So I'll save this later on, and that's another day. Said, let's take a look. Let's analyze that again. You could actually click on that and tell it to identify which value it was, like data number 43, which row it was, and you could actually go into the double click on it and have it uh, actually label all of the different dots on there as well. Okay, so you can if you go into this SPSS and actually start working with it a little bit, you can get a pretty good idea of what you can do in terms of customizing these charts. So I'm going to go back in here and I'm going to do the same thing again. Okay, and let's see how it looks now. So now I can look at this, don't I? There's a couple of lessons to be learned here. One is that when you have outliers like that, it can compress the data, make it hard to improve it. The other is that you can kind of fool yourself a little bit if you change the scale. Like in other words, right down here on the bottom, the unemployment rate, if you look at that, that distance is 1%, right? Now, and the slope looks pretty strong, right? Looks like a 45-degree angle there. Right? So now, that's interesting, but if I made 1% that wide, well now, the unemployment rate is still the same, it's increasing the same height. It makes the slope look a lot flatter, right? So it's easy to look at these graphs and be fooled a little bit. You got to keep in mind that the scales that you're using can change the way you might interpret them, can alter the way you might interpret them. So you got to be a little bit careful, keep an eye on that. Okay, so let's see what that formula is going to be. Analyze, regression, linear. Okay, so again, let's see, single unemployment and murder rate. Okay, see what we get. Okay, so now, what is our R value now? It's 0.351, right? Seems like it seems like an interesting idea that, like, gee, there what seems to be some correlation, not a perfect correlation, not that strong a correlation, but some sort of correlation. Well, how predictive is the unemployment rate on the actual murder rate? Well, R squared tells us that 12% of the variability between states in the murder rate is associated with the poverty rate, with the unemployment rate. So, gee, that's, there must be a lot of other factors that are impacting that, because 88% is associated with other factors. Let's try another variable. How about poverty? See if that's a stronger association. Okay, what's our R square R there? Oh, well, this looks like a bit stronger of an association. Now 18% of the variability in the murder rate is associated with the poverty rate. So now we have a formula. If you go down here to our constant, this formula that we calculated before suggested that the murder rate is equal to 0.93 times the unemployment rate plus 0.972. That's a formula that I might have generated in that case. And that would explain, I think it was 12% of the variability in the murder rate. I go down here, and my new equation is the murder rate, the poverty rate times 0.365 plus 0.432 is equal to the murder rate. That's what I'm predicting with that line. Okay, well, but this is a little bit more predictive. It's 18%. Let's combine the two of these and see what it looks like. Okay, we got poverty rate in there, and let's put the unemployment rate in there, and let's do this again. Okay, and now we have a number that's larger than the both of them. In other words, by putting these two values together, we wind up with a situation where we have a formula. Now, formula is going to be a little bit more complicated right now, right? So going to be the poverty rate times, we have two slopes, the poverty rate times 0.286 plus the unemployment rate times 0.441 plus this constant, and that new formula is more predictive. It predicts 20% of the variability in the murder rate. Okay, it didn't add up too well. It improved the poverty rate prediction, but not that much. Why do you think it didn't improve the poverty rate that much? What do you think about unemployment and poverty? They're already associated, right? So really didn't help us that much. Let's try some other analysis. Analyze, correlation, regression, linear. Okay, let's try a couple of things that are not so direct. Which was better here? Poverty was a better predictor, right? Okay, so let's try single parent households. Percentage of single parent households. Okay, and in this case, look how much that's improved. So now we have an association, and when we put it together in the multiple regression, is a much better predictor. Now we're predicting almost 50% of the variability in the murder rate with a formula that associates single family, the percentage single parent homes, and the poverty rate with the murder rate in each one of these states. And that's a pretty good, isn't that pretty good? Our correlation is 60.69. And I'm going to blow that up so you can see it better, since this one worked out so well. So now, this might be something that you might be doing with your project, right? You're going to have to look at the variables that you have to work with. What kind of no. I have to do this because SPSS doesn't behave well, and it won't let me just like expand the size of the size of the window, blow it up just by clicking on it. Oops. And that's that one. Okay, good. Now I should be able to do this. Okay, so what do we have here? R is 0.691. Was never higher than, I think, 30%. It was 0.30 before. R square is 0.477. 48% of the variability in the murder rate in the states can be predicted with these two variables that I associated with it. And if I go down here, I can see that I got a little bit of a problem here, don't I? I have the slopes here, right? What is the problem that I have here? That the significance for the slope associated with the poverty rate is not statistically significant, right? So now why did that happen to me? Remember we had a rule that you have to have at least 10 cases for each variable that you're going to put into the multiple regression, like you have 70 out of 70 cases and so on, even to use it at all, because it's very sensitive to sample size. So our sample size, even though it was like 50, it's a pretty small sample size still, because we only have 50 states. We can't go out and like sample more states and things like that. But I got a little bit of an issue there that didn't suggest that this was a statistically significant association. In other words, the variability might have been so great in the poverty level and versus the age versus the murder rate, the variability between those. And I think if you probably plot those individually or scatter plots individually, you'll see that illustrated there. Yeah. Yeah. That's poverty rate and single parent, they're probably associated also, but probably not as strongly as when we examined the other, which didn't show us a big improvement in the multiple regression. Okay. All right, so it's 7:50 now. So I think it's a good time to take a break. So yes. I'll tell you what. Let's discuss that during one of the online sessions, right?